Hello everyone, so welcome to my channel. So in these videos we will continue our materials of statistics, and now we move to a new materials. So this is about the design of the experiment. So why people do the design of experiments in statistics? So experiments, generally we say this may be about some engineering, about the medicines, about the some other topics, but in the statistics, what we want to do is we want to use a reasonable experiment to check about a relationship. So for example, if we want to know one medicine, this is works over one disease, what we should think about. So maybe you think, okay, for one or for several patients, give them this medicine, and then we find that this people is recovering, and we conclude that this medicine is works for this disease. However, this one is not correct. Why? Because for the patient, at the same time, maybe these patients will recover by themselves no matter we give them medicine or not. So like some flu or some mild disease, or others in the same times they maybe also take some other medicine to try to recover or try to fight with this disease. So in this situation, just look at the data or just look at the result of some unsafe experiment, we can have a very totally wrong conclusion. So in this one, before we try to analyze this or try to deal with the data like we do in the previous videos, to do it in the hypothesis test or do the estimations, the first thing is when we try to get the data, there is one thing is we need to know how to design an experiment to get a reasonable result. So in this several videos, I will talk about these topics. So first of all, let us look at one simple situation. This is the single factor experiment. So for this one, this situation is we only focus or we only want to test one factor or response at different levels. So here, for example, we can assume if we have the patients, all of them have the same health conditions, all of them have same food and do same exercise, and then we just different their treatment. For example, one drug at different dose. Then we want to check about what the treatment or will the patient get healthy. So let's look at some example here. So here for this one, we will have focus on what is a treatment and then what is a response. So for example, we can have the treatment as we said about the drugs or medicines. So here we can have this is a one factor here. This is a one factor here, and then we will have three levels. So this means we use the low or medium or high the dosage about this drug. And then the response or the result we want to check is about the illness, like be the patient become better or not. And then this can also be many examples. For example, about manufacturing, about the concrete mixing technology. And then this is need to be only one factors, and they should have several levels. And then the response is how about the strength of this project. And also if about the students, then this is about the study skills. But of course, there are many things will affect the study skills or including to study skills, right? It's like the time you spend on study and the materials you use and about the style, like when or how you should study. But remember, this one is about the single factors. So you need to differentiate this to one single about several different levels. So here we just talk this about like the primings or discrete, and then the most obvious response about this for the study or student is about the test score, right? So this is about some examples for the single factors. And then what we will have now, so when we have um, this experiment or the questions in statistics, the first thing is we should use some symbols to denote them, right? To translate this to the mathematics. So now let us denote the number of the treatment as a small letter A. So here this means, for example, if we talk about the medical experiment here about the drug, then A should equal 3. And if we talk about the study skills, this means the A will equal 2. And of course, if we talk about one of these treatments, so for example, if we order about the drug from the low to medium to high, so low is the first one, so we denote it by I equal 1, medium is second, so I equal 2, and the last high dosage is the last one, the third one, so we have I equals 3. So here I is about the index for one of this treatment, and is of course below the number from 1 until A. And then for the eyes treatment, then we will have the observation, or we say the data for it. So we denote the numbers of the observations as the eyes treatment as Ni. So for example, if we have 10 patients receive the drug with a low dosage, then we have this N1 because low is the first one, so N1 is equal to 10. And for the median, the second treatment, maybe only 3 patients, then the N2 is 3. And then for the last one, the high is our N3, it can be another number. So here for this single factor experiment, it not means for each treatment we will have exactly same numbers of our observations. It can be different. So that's why for this N we have a sub I to denote it. This is observations for this eyes treatment. And about this observation, of course we should have a notation for this one. So we denote this by Y sub ij. So here J is a J's observation at I's treatment. So for example, if we have 10 patients and we order them by 1, 2, 3 until 10, and then the first data selected from the first patient as a lower level of our drug, then this is our Y11. And the second patient as a low level is Y12. So here 1 is for the first treatment, and 2 means the second patient, second observations from this or at this treatment. So now we have these notations. So what we can have, we can write about models, or we say about equations about this data. So equation is Yij is equal mu I plus the epsilon I. So mu and epsilon ij are all the Greek letters. And then for the mu, this is our sample mean as an ice treatment. So this is our notations. And then about the epsilon. So previously when we talk about linear regression, we also have a symbol epsilon here, epsilon there. So we use that one to denote about the errors. So here in this part, the epsilon is same. This is still about the errors. So this is random errors, depends on the treatment. So that's why here for our epsilon, they have the sub I, and J is for our observations. And in our previous linear regression, we talk about for the epsilon term, generally we have some assumption about them. For example, the mean of them, the variance of it, do they independent with or and correlation with each other, or do they follow some special distribution? So here in this part, we also have very similar assumptions about our error term. So here what we have this one is still follows about a normal distribution, and with the mean is as 0, and the variance is sigma I square. So here this means for different treatment we will have different variance, but all of this, no matter which treatment, we always have this mean is equal to 0. Okay, so this is about our models or equations about our Yij. And here one more thing about our mu I here, the sample mean here, is for our mu I, of course we have I here because this will be different for different treatment, right? But then how about overall result? So for example, if we talk about one drugs to heal one disease, then no matter what the dosage we need, then they maybe have an average percentage people will recover. So this one is independent with any lower or medium or high amounts we use. So for this one, we denote this by mu. So that means here for our mu I, we will have an equation plus mu overall mean plus the tau sub I, which is in fact of the I's treatment. So here for this one, this is an equation about our sample mean here. So here about this one, we still have one more assumptions about our experiment. So we already say for this experiment is only single factors, right? So every other situation are exactly same. The background of the patient is exactly same. But then for the experiment, we still have one more assumption. This is about the random. So here for this experiment, we assume this is a completely randomness designed. So that means here, all of our Yij, they should made randomly order, and they should have the similar environment. So this is assumptions. And then in our following videos, we will assume all of the observations of our each treatment are same. So that means here for our n sub I, so this will equal exactly same values. So for this one, of course, this is not required for solve or talk about the materials in this design experiment, but we just for for simple to write down it in these videos. So then after we have the observations, also the data about the single factor experiments. So if there's some questions we can answer by this data. So here for this one, so the first one is in the previous when we talk about the model, we already say this mu I. So this mu I may be different for each of the treatment. But this is just a guess. It could be different, it could be same. So the first question we can play with our data is we want to test if this mu I is same or is changed or varies by the treatment. So here, this is of course something about the hypothesis test. So because we say something equal some mu equal something or not, so this is about a hypothesis test. So in our previous videos, we already talked about the hypothesis about if the distribution follows a normal distribution, and then we can know like the mu1 equal a number or not, or we say if we have two samples, we say mu1 is equal mu2 or not. So here for this treatment, if the number of our treatment is 2, then everything is exactly same with our previous videos about hypothesis test for 2 samples. So let me write down about this one. So if we have 2 samples, we have mu1 and mu2. For this hypothesis test, we always have the non-hypothesis H0 is about an equation. So that's why here this is about mu1 equal mu2. And then for the alternative hypothesis H1, so we always say they can have the 3 cases. So the unequal means two side tests, greater than or smaller than, so two one side tests. So here I just write down the two side tests just for example. And then for this one, you can review our previous videos, right? So I won't repeat exactly each step of this one. But the idea is we need to construct a statistic, test statistics. And for this one is maybe depends on do we know the variance, the sigma or not. If we know it, it's about a z-test. If we don't know it, it's about a t-test. So generally, like if we don't know this sigma, then we will have a t-test. So let me write down a note here. So this is about use the t-test to check about our mu1 is equal mu2 or not. So of course, this is one way to check about the effect of the treatment. But they also have another one is if we want to know about the virus. Of course, it's not exactly like how many percentage of people can can recover after they take this medicine for different dosage. But the also interesting question is do they have very different of this performance of the drug? One dosage of the drug, it really depends on the personal, on the patients. So this is about to describe the difference for a population or to a sample. This is about the variance. So for here, the other thing is we can also do a hypothesis test about the variance. So by this one, the only difference is now we talk about the sigma square, sigma 1 square and sigma 2 square. But the idea is very similar. It still use a hypothesis test about two samples. And then you can look at my video about the hypothesis test about two samples to get how to do this one. So this one is about if we only have two levels or two treatments. So for example, about the study scale, we only have the screening and also about the discrete. But then for if we have three levels like low, medium or high of the dosage, then the question is a little tricky. So for this one, what we should do, one idea is we know how to do it for a pair of the sample, right? So one idea is we can do each pairs of our three levels. So for this one, it means we can use the pair low and medium, do one hypothesis test, then do it for the medium and high, do one hypothesis test, and then do the low and high as the last pair of the hypothesis test. So we can write down this as this one. So here we still have the equation for our non-hypothesis test and hypothesis and H0, and then for the alternative hypothesis H1 is it just write the two sides equation here. And then the idea is still similar. When the variance is unknown, so we can use about the t-test. So here for this case, let me just write down one example. Just write down the one t-test statistic here. So this is our t-test statistics when we talk about the S treatment compared with the case treatment. So here, of course, the X bar is about the sample mean and the S square is about the sample variance or the error term. So here, if you want to know more details, you need to look at my previous videos about the hypothesis test. But the main idea of this one is we need to do the pair of the hypothesis test. Right? So I already say if we have three treatment, low, medium, high, we need to do three hypothesis tests. Low with medium, medium with high, and low with high. And if we have four, Then we have the first one with second, then with third, with fourth, the second one with third, with fourth, and the third one with fourth. So you can know for this one how many tests we need to know. So this is if you look at the materials, we talk about the numbers of the elements in the sample or event or in the sample space. Then this is about something we call it about the combination. So previously we use this parentheses upper top A and bottom 2 and close parentheses to show this combination. So it's kind of like we select 2 items from total A items, right? So we talk about this already in our previous lectures about this combinations. But then, of course, this is about in the numerator is a of our factorials and divided by the a minus 2 factorial and 2 factorial. So this number can be really, really large when we have a really large value of a. So in this situation, so there is too many tests we need to finish to check about the effect of the treatment. And also in the lectures about hypothesis tests, we also talk about the type 1 error and type 2 error. Right? So if we have so many pairs of the hypothesis tests, and then if we talk about the experiment-wise error rate, so it means what we will do is kind of combine of all of the type 1 errors together for all of the tests. So this could be a kind of really large value. So here I just write down this equation here. So this number can be pretty large when we have a large A. So based on these 2 reasons, too many tests, too noisy, and also about the error is high probability to have the error type 1 error for at least one of these tests. So what we want to do is we want to do a test. This test can check about the relationship between the mu1 until mu8 together in one test. So about this one, this is about the ANOVA or the F test. We briefly touched about these materials in our previous video in the ANOVA part, but in my next videos I will talk about how we can use ANOVA and also F test to help us check about the equation or hypothesis mu1 equal mu2 until equal mu a at one test. So see you in my next videos, and please subscribe my channel, and I will talk more about these materials. So bye.